So when you're discharging a capacitor, the capacitor starts with some maximum charge, and then as time progresses, the current I will go through the resistor R and discharge this capacitor. Now the graph for the same is like this. It starts with the Q maximum, and then the current, you can see the current is the slope of this line, which is a negative slope. So the value of I maximum is going to be V over R, the maximum, and that is going to be negative Q over dt. The magnitude is negative dQ over dt. And with respect to some time, so by the time some time passes by, this charge goes from Q max to Q. So bringing Kirchhoff's first loop rule into account, starting from here we have positive VC and then a negative IR equal to 0, so VC equal to IR, but the I itself is negative dQ over dt times R. Q. V, the voltage across the capacitor, we are replacing with Q over C from the expression Q equal to CV. And then we got this, and then we are bringing all the Q's to one side and then time to the other side. We got this one now. And from that step, you integrate Q with respect to Q with the limits starting with Q max to Q. And the time that passes by is 0 to t. So we got this. Now you can combine these two by that. Right? Log A minus log B is equal to log A over B. Right? So that's A over B sort of formula, and this is minus T over RC. Now when you say natural log, what is the base here? E. So if I want to get rid of this natural log, what is Q over Q max alone? How do you get rid of logs? Take both sides to the e power. So e to the power of all this will get you only that part of it. So Q over Q max. So e to the power of this is going to be just inside part. So e to the power of minus T over RC. And therefore Q is equal to Q max times e to the power of minus T over RC. Don't have to worry about what's going on. This is the equation we will end up using. What is this equation for? This equation tells you how much charge still remains after a period of time. That's what this equation tells you. How much charge remains? How much charge remains after a period of time t? So highlight that equation. That's an important equation. So Q is equal to Q max e to the power of minus T over RC. Now, if Q is equal to Q max e to the power of minus T over RC, and if you substitute Q in terms of the voltage across the capacitor and the capacitance, what is Q equal to? CV. So CV is equal to CV max e to the power of minus T over RC. Now you can divide both sides by C. So C is gone. And so we have V equal to V max e to the minus T over RC. What does it mean? That means you can plot a graph of voltage across a capacitor with respect to time. The voltage across a capacitor with respect to time, or even the voltage across a resistor, it's going to be the same thing. So the capacitor is seen to be discharging, and the amount of time it takes to discharge. How much time does it take to discharge? Infinite. Because it doesn't end up, It's supposed to reach the x-axis only at infinite time. So capacitor discharges after infinite time. I think in chemistry you must have done something called half-life. We will do that again here. But what is the concept of half-life? Or what is full life? Full life technically is infinite. And what is half-life definition? Huh? How do you define half-life from chemistry? Yeah. Decay. The amount of time it takes for half the substance to decay. That means if you have 100 grams of radioactive substance, how long will it take to make it 50 grams? So that is called half-life. Similar to that here, we don't define half-life or half-time. Instead, we define a different kind of time. It's called time constant. Write down the definition of time constant. Time constant. So time constant is a term that is used in capacitors. We don't use half-life. What is time constant? It's symbolized by the letter, what letter is that? Tau. That is tau. It's a Greek T. Okay? The Greek T. It doesn't have the top part, that's all. See this time? So the time constant tau is defined as what? Write down the definition I'll give you. It's a time taken for a capacitor. It's a time taken for a capacitor to discharge to 1/eth. Time taken for a capacitor to discharge to 1/eth. eth. Like 1/9, right? What's 1/9? 1/9. 1/eth. 1/8. Yeah, 1/eth. Just like 1/9 is 1/9. 1/eth is 1/e. Off. So, what is the definition? Time constant tau is defined as a time taken for a capacitor to discharge to 1/eth of the original, the initial charge or potential difference. It's a time taken for a capacitor to discharge to 1/eth of the initial charge or potential difference. So what is tau? Tau is a time taken for this to become 1/eth of this. You get it? So taking that expression, Q is equal to Q max e to the power of minus T over RC. Now, what is time constant tau? If I'm going to put tau instead of this, then the expression becomes Q max over E is equal to Q max times e to the power of minus tau over RC. That's a Q max, and that's a Q that is after a period of time. You want this to become 1/eth of the initial. The initial was Q max, right? The initial was Q max. Before you started the discharge, it was Q max, the first one. The Q initial. some books write it as Q naught, some different Q initial, QI, so Q final, Q initial, different symbols can be used, but yeah, the main idea is this. If it starts with a certain maximum charge Q, then this Q is going to be Q max over E, and then the tau is going to take the place of T, right? And you can see that these two is gone, and this is now e to the power of minus 1 is equal to e to the power of minus tau over RC. Correct? So what is minus tau over RC? That's negative 1. So what is tau? RC. Tau is RC. Tau is measured in what units? Seconds. That is in seconds. Resistance is measured in what unit? Ohms. Capacitance measured in farads. So ohms times farad is seconds. Ohms times farad is seconds. The product of ohms and farads is seconds. Now, if you want to know why it is coming out seconds, break down ohms and break down farad to the basic, and you'll see how it comes down to seconds. I'll show you that right now. So, ohms times farad. Ohm is what? What's the unit of ohm, like breakdown? Volts over amps, right? Volt over amp, that is ohms, right? Volt over amps is ohm. And farad is what? And C is Q over V. So what is farad? Coulombs over volts. Now these are gone. So what is happening now? What is coulomb? Coulomb is ampere second, and then ampere, and finally it comes to seconds. Right? You see it now? So the ohm times farad is seconds. You can see how it works out. You don't have to fully break down because volt and volt is gone. Otherwise you have to bring in the joules per coulomb and all those things in. So what is time constant? It's the time taken for the capacitor to discharge to 1/8 of its initial charge, whatever it started with. And the time constant is easy to find out. It is R times C. So for example, if I have a 1000 microfarad capacitor and I charge it fully, let's say I charge it to 10 volts. I charge it to 10 volts. And then I connect to it a resistor of 1 mega ohm. I connect a resistor of 1 mega ohm. What's the time constant? A 1000 seconds. After 1000 seconds, then this voltage from 10, it will drop to what? 10 over E. What is E? 2.728, something like that. You can check it out, e to the power of 1. If you put e to the power of 1, it will give you that number. So basically what's going to happen is, at time t equal to 0, the voltage was 10. at time t equal to 1000 seconds. So tau equal to RC, which is equal to 1000, 1 mega ohm, 1 10 power 6 times 1000 times 10 power negative 6. So that's how you get 1000 seconds. So after one time constant, the voltage goes to what? 10 over e to the power of 1, right? 10 over e. How much is it? 3.68 volts. So after 1000 seconds, it drops to that much, yeah.
So if you were to find it at the second interval, then would that be e squared or 2e?
E squared. So at time equals 2000 seconds, that means one more time constant has passed by. Now the voltage is going to be 1/eth of what was existing, right? So this is what was existing, and now 1/eth of that. So it becomes 1/eth of this becomes e to the power of 2. And how much is that? So basically divide this with e once again. 1.35 volts. And then at time t equals to 3000 seconds, this becomes 10 over e to the power of 3, which is 0.49 volts. And then it goes on 4000 seconds. The voltage is 0. How much is 10 over e to the power of 4? Point 0.18. And you can see it goes on like that. Now if you sketch that on a graph, you'll get the actual shape of that graph just explaining all this. Now that is 10 and that is 0. After one time constant, after one tau, which is 1000 seconds, the voltage comes down to 3.68. That's 5. That is 3.68. That's after one time constant. After two time constants, the voltage comes down to 1.35. So this actually is 10 over e. And then after that it becomes 1.35. So 10, 5, 1.35. And then after three time constants, it becomes 0.49. 9. And after 4 time constants, it comes down to 0.18 and keeps going like that. So that's why the graph is shaped that way. So that's a discharge graph. And you can see numerically how you have connected it up. You saw the actual equation for it as to how it goes on, and now you know what is time constant. So time constant is a very important part of any timer circuit. Okay, timers. We use timers in so many places. So many places we use timers. Like for example, if you're walking out of the door senses that you are present, right? As soon as it senses that, it gives the relay trips to the other side, giving the voltage to the door lock. So the lock is now unlocked. So you are able to go without any problems. So the door is open for you and goes. And now the door closes. There is a little period of time. It waits before it locks. And that is controlled by timers. So as soon as it senses you, as long as you are being sensed continuously, the voltage is kept high. And the moment you cross over, you're not being sensed anymore, then the timer starts timing down. So the timer and the circuit goes out of operation after the voltage drops to some value, right? But of course, it's not 1,000 seconds. 1,000 seconds is a lot. It can be just a couple of seconds. Okay. Now, what will happen if I make this 1 kilo ohm? One second. So the time constant is 1 second. If I make it 1 kilo ohm, connect a 1,000 microfarad capacitor to 1 kilo ohm resistance. So 1 kilo ohm is 1,000 ohms. What will happen is, after 1 second, it drops to 3.68. After 2 seconds, it goes here. After 3 seconds, after 4 seconds. So by a couple of seconds, everything is over. You know, it just discharges very fast. Now, what if I put zero resistance here? So time constant is 0, which means like instantaneous, right? And that is why because it's instantaneous, it pushes out all the energy in one go. And that's why you see that. Questions here? Now, what is the difference in charging? When you're charging it, then you have a battery coming inside. Well, you don't have to know how to derive these things, but I can derive it if you want to. So when you're charging a capacitor, what's going to be the difference? When you're charging a capacitor, you have a power supply that is connected. We are connecting an EMF to the capacitor, and of course through a resistor. So what is happening over here is the capacitor initially has nothing, has no charge and no voltage. Initially it has nothing, and then as time passes on, it will start accumulating charges. Now the expression for that, I'm not deriving it, you can derive it by using again the same Kirchhoff's laws. When you use Kirchhoff's laws, now extra term comes in as E. But what is E? E is a maximum voltage. And what's maximum voltage? Maximum voltage is the maximum charge over capacitance. Maximum charge over the capacitance, that's going to be the EMF. So we bring that maximum charge into our expression, and then the expression finally turns out to be this. The charge that remains after a period of time is going to be Q max times 1 minus e to the power of minus t over CR. So if you put time t equal to 0, what happens here? If you put 0 over here, no.
Yeah, because then it'd be 1 minus 1, and then it'd be 0 times Q max. So then Q equals 0.
Q won't be 0. Oh, yeah. Charging, yeah. Time t equal to 0, 0. E to the power of minus 0. Basically, if you bring it down 1 over e to the power of 0, anything to the power of 0 is 1. And so finally you get 0. Now, as time passes on, you can see the charge building up. That's a charge. That's a time, 0. After one time constant, what is the Q that's going to exist? It's going to be 1 minus e to the power of RC over RC, right? Correct? Which is e to the power of -1. So when you say e to the power of -1, it is 1 minus 1 over e. In other words, it is Q max minus Q max over e. Q max minus Q max over e. Correct? So in other words, not this, but 10 minus that. You get it? Q max over E or V max over E is this one. But we are now talking about the V max minus the V max over E. So 10 minus 3.68. So it's going to be what? 6.32. Right? So 6.32. So what's happening is in one time constant, the charge builds up. Now that's a maximum 10 volts. The charge builds up to 6.32. Now it's building up. After two time constants, it's going to be 10 minus this. So it's building up further. Somewhere here. And after three time constants, it's going to be closer to 10. This is this. It's almost like 9.5. After four time constants, it's almost going to be 9.8. Right? So after four time constants, it's going to be close to there. So the graph goes like that. So that's a charging graph, where the charge builds up, and the expression that controls it is this. That's the equation that we use to explain how a charge is building up. And what's the expression? So we have two expressions now. One is for discharging of capacitors, and this is for charging of capacitors. Yeah.
So can you ever really charge something fully?
Practically, theoretically, no.
Okay.
Theoretically, no. But you see, after four time constants, you're already 9.8 volts. So if you just keep on waiting for some more time, it is going to reach that brink. And so
even when our friends say 100%, it's not like truly 100%.
No. No, it's not. Theoretically not 100%. Yeah.
I've seen other constants.
R is a constant which is ohms. C is both are constants. Resistance and capacitance both are constants. What I'm trying to do is this. I'm trying to set up a circuit where I'm going to set up a circuit like this. Look, that is a power supply. I'm going to use. This one is capable of handling 16 volts. I'm going to just use 6 volts. So I'll use 6 volts, and I will charge a capacitor like that. And I'll put a resistance like that in parallel to it. So the resistance I'm going to put right now is This is so bad. Can you tell me the colors here? Can you tell me the colors? What are the colors from this side?
From left to right.
Yeah,
It's
from
like magenta, black, orange, and brown.
magenta.
Yeah, it does look kind of like magenta and maroon. Very left.
It's
like a red.
It's definitely brown, bro.
Right?
Huh?
Yeah.
I thought the right was like.
The left, very left is brown, and like the very right is like gold.
Okay, that's good.
It's brownish.
You
You
got
don't
it.
know your colors. Kidding.
Yeah.
I promise you I'm not
So-
really blind.
Yeah, the very left is brown. So brown and then black, right?
Yeah.
Brown, black.
I didn't
Orange?
know the rest.
It was like gold,
It's like red.
Is it brown, black, and
Yeah.
orange, or what?
black, orange, gold.
Yeah, it's definitely orange.
Okay, we're looking at it this way. It's brown, black, orange, and gold.
Okay, brown, black, orange means it is 10 kilo ohms. That is 10 kilo ohms. Brown is 1, black is 0, and orange is 3. So 1, 0 times 10 to the power of 3. So this is 10 kilo ohms. So what I'll do is I'll connect 10 kilo ohms here. And this one is 1000 microfarads. It's 1000 microfarads, but very small because it's only capable of handling 16 volts. But I'm not going to put too many volts into this. So that should be good enough. So I'm going to connect this up. And when I connect it, what will happen is the 6 volts will go straight up here, right? And then what I do is I disconnect it. When I disconnect the battery, what happens then from here to here? It's discharge. And I'm going to connect a voltmeter right across. So the voltmeter will measure the potential difference across the capacitor. This is what I'm trying to do, but unfortunately, oh yeah, I have some wires here. So it's doable. So I'm just going to do that sort of wiring before I do anything. So positive, that's a positive, and it's supposed to go to the positive of the capacitor. So that's a positive of the capacitor. So that's done. And then I need a wire to connect the negative to the negative of the capacitor. So the negative goes to the negative of the capacitor. That is done. What do I need to do after that? So this part is done already. So to discharge it, I just have to disconnect one of them. Okay? If I disconnect one of them, I'm beginning the discharge process. Now what is to be connected across the capacitor are two things, the voltmeter and the 10 kilo ohms. So that's a 10 kilo ohms. I need to connect the 10 kilo ohms. So I connect it like that, like that, to this. Doesn't matter, any polarity is good. So the 10 kilo ohms is connected across. That's done. And then I need to connect the voltmeter across the capacitor. So the positive of the voltmeter should go to the positive, and the negative of the voltmeter should go to the negative. Now, positive is right there. I'm going to plug this in somewhere. That should stay. Positive connected, and the negative.
Just like.
Yeah, I need to have that connected also. So I can do this. I can probably connect it like that. And this. Okay. That one will be connected. Yeah, I can hold it. I can hold it. So, all right, I'm going to turn it on. I'm going to turn it on and I'm going to charge it first. Charging won't take much time at all. It's going to be immediate. Charging won't take much time. It's going to be immediate. Oh, there it is. Okay. Charging won't take much time, so let me put it for charging. So if I touch it here, it should begin its charging process. Well, it's showing more than the required voltage. Anyway, it's showing around 9 volts, 10. You see it? Now, before I do anything, find out the time constant for this. What's the time constant? How many seconds is the time constant? How much?
It's 6
What is the time constant for this? 10 kilo ohms times 1000 microfarads. 10 seconds. So after 10 seconds, after every 10 seconds, the voltage is supposed to go down from 10, it's almost 10, right? From almost 10 to 3.68 after 10 seconds. So you can monitor the time if you want, and you can see how it's going down. Alright? So I'm charging it first. Now it is charged. It starts with around 10.11. Oops. It's starting around 10.1, and I'm going to take it off. So it's 10 volts, approximately 10 volts. And when I take it off, after every 10 seconds, you can keep a stopwatch and see how is it matching. After almost 10 seconds, it should go to 3.68. So the time starts now. Oh. Time started, but the voltmeter got disconnected at the same time. Okay. Yeah, that's why we need both. This is why it's not. Oh. No big deal. Okay. I'm doing it again. If you want, you can start a stopwatch on your phone. So after every 10 seconds, you can just see what's happening. I'm charging it again. Back to this. Are you timing? Okay, just say when 10 seconds are over. Okay? Ready? Start now. Right now, over? Yeah, so that was 3 point something. Next is 1.35, approximately. So after 20 seconds should be 1. I'll tell you when it's 1.35 here. 1.35. 20 seconds over? Okay. Yeah, first of all, the voltage is not exactly 10, so that makes a difference. If it is 30 seconds, it should be 0.49, approximately 0.5, yes. Was it 30 seconds?
Yeah.
And after 40 seconds, it should become 0.18, which is almost no. Okay, so you see how it's working? So the voltage is coming down, and it's coming down exactly the same way as we have shown. This was showing some other direction. Okay. I don't know if I'm doing it again. It starts right now. That's full, right?
Yeah, 10 12.
And then start discharging. And you can see as time passes by, the voltage is coming down. Okay, so it's almost 10 seconds now. Okay. Now, what if I change the resistance and change it to, what is the other one? I've got the color problem. I'm replacing the resistance with the new one. There he is. I'm replacing the resistance with the new one. Now, I'm going to charge it once again. Now what's going to happen is after every 200 seconds, it's supposed to come down to 1/8 of the value, which is 3.68. So I'm charging it again to max. Is it already charged to max? Yeah. See, it doesn't take much time to charge because there's nothing here, no resistance here. So it instantaneously charges. The moment I touch it, it's already charged. Now, when I disconnect it, the timer starts now. Ready, steady, go. Now you can see the thing is coming down. You can see how slowly it is coming down. After 200 seconds, it's supposed to be 3 point somewhere here, almost 3.7. After 200 seconds. So it's discharging at a much slower rate. You can see that very clearly. Are you timing at all?
Yeah.
Okay. It should be approximately there because those components are not of the highest quality. They're all like pulled out components from here and there. So, and the capacitor also has the weight.
It's like
45 seconds. 45 seconds. Now, 200 seconds means almost 3 minutes. We can do something useful by that time.
More than 3 minutes.
Yeah.
It's 3 minutes and 18 seconds.
3 minutes and 18 seconds. Okay.
This is the most bootleg setup circuit up here.
Yeah, it is. The thing is, it's all wired up.
Alex, come to my house, you'll see my computer made out of jumper cables.
Now still going down. So almost 3 minutes and 18 seconds. That is. How much time now? 3 minutes 30. So that is a good capacitor. If that was a bad capacitor, it would have definitely shown a different timing. So one way of checking if the capacitor is good or not is hook it up like this and check the time constant. The time constant is as anticipated, like the time constant of these two is exactly 200 seconds. That means the capacitor is doing the right thing of discharging at the right pace. Now if the capacitor is bad, it's a shorted capacitor or something like that, the charge won't stay. It will just discharge very quickly. So it is not holding a charge. Yes?
What kind of margin of error can you expect from a good?
Oh, there is plenty of margin. This resistor itself, gold, means 5% tolerance. Which means what? When it says, how much is it? 200 kilo ohms, it is not necessarily, it's 5% up or down. There's a 5% error in this straight away. And when they say 1000 microfarads, again there is an error possibility there. So there is a, how many seconds now?
2 minutes 45 seconds.
And it is still on its way down. So it should come to almost 3.7. 3.8. How many seconds is it supposed to be? 320.
Yeah, 3 minutes, 3:18.
It's almost now.
I think 3:10.
Okay, so we are close. So with the tolerance included, it is doing the right thing. It is just discharging at the right rate.